Okay, I'm going to try and wrap this up as a fourth video and call it a night because it's getting late. You should probably be in bed by now, anyways. But okay, so what we're going to do is we're gonna take the chemical name and create a formula using the same sort of rule that we used before. That the mono is 1, di is 2, tri is 3, and all of these things. So here it says diphosphorus pentoxide. So di, there's 2, so it's and it's phosphorus, so it's P2, and pentoxide, it's oxygen, and 5. And it's that simple. Dihydrogen dioxide. I've got 2 hydrogens, 2 oxygens, because 2 hydrogens, 2 oxide ions, or not even ions. Carbon monoxide. So I've got carbon, there's only 1, so I don't write a number. Monoxide means there's an oxide, but there's only 1, so I don't write a number. So CO would be our formula for carbon monoxide. Tetraphosphorus deca, deca I forgot is 10. 10 is, let's go back, we'll get this. 8 is octa, or octo. 9 is nona, or nono. If you're Italian, it looks familiar a little bit. And 10 would be deca. Yeah, we won't go into 11 or 12 on deca and dodeca. But tetraphosphorus deca oxide, I'm hoping this won't be in there, but I don't recall if something like this was there. But if it's there, you know what it is. So tetraphosphorus, phosphorus, there's 4. Deca oxide, there's oxygen, and there's 10. So P4O10. Okay, now here's the real thing that I wanted to do. Don't worry about any of this, the periodic table and periodic table trends. Again, that's grade 9 stuff. But what I want to do is I want to look at this balancing equations, because I know that's going to be a tricky part for most people. So what I want to do before we get to that is, I'm not sure who planned this, but this C2H6, this is, if I'm not mistaken, I don't even know what it is, what the chemical name for this is, but it's a hydrocarbon. We would use it as fuel. It's possible to do this, and we could balance this equation. This is a very tough one to balance, and I don't think you in your course you'll have to deal with something that tough. But it is an important type of chemical reaction, so I want to keep it, and we're going to work on this. So what I'm going to do is I'm going to get rid of this first. In fact, let me use a white pen, if it does it, and I'm going to change the pen settings to white. And so let's just draw over that C2. So we'll get rid of that. I'm going to draw over the 6, get rid of that, so it looks better. And then I'm going to go back to this. So I'm going to call it, we're going to have CH4. This is methane. Okay, so CH4 is a fuel that gets used. We're going to use that one to balance. So that's the first thing I want to do. The second thing I want to do is I want to clarify some terminology on for any chemical reactions. We're going to start off with what we call the reactants. Sorry, this reactants on the left side. The reactants are on the left side. So this is called the reactant side of the equation, and these are the products on the right side. So this is the product side of the equation, and you'll see why I need that in a second. So what we want to do is all chemical reactions obey what we call the law of conservation of mass. So conservation of mass. Okay, and what that means is whatever mass I have, and the mass is created by the atoms. Okay, all of the mass is in the atoms. whatever mass I have on the reactant side, I have to have on the product side. And the only way I can guarantee that this in a chemical, not guarantee, the only way I can describe that in a chemical reaction is by looking at the number of atoms. So what this means is whatever number of atoms, if I've got aluminum, I've got hydrogen, sulfur, and oxygen on the reactant side. If I look at the product side, I've also got aluminum, I've also got hydrogen, I've got sulfur, and I've got oxygen. I've just got it in different combinations. So what I want to do is I want to look and say, I do a bit of accounting. I'm gonna count up the number of atoms on the left side, the number of each type of atom. On the reactant side, I'm going to count up the number of products on product atoms, like atoms on the product side. I want to make sure that this is conserved. This is this conservation of mass that we know we've seen. We call this a law, and it is a law because whenever we do these chemical reactions, and we can account for all the stuff, if, like, for instance, hydrogen sometimes escapes, so we have to make sure that we trap it in our system. But if we can trap it and account for all of the reactants and products, then the whatever mass I had before the reaction is always equal to the mass that I have after. And again, we call this a law. This is called a law because it's something that happens over and over and over and over again. We don't know why, it just does. And so because it does, we make that observation. We recognize that it always does. And if that sort of rule is never broken, we call it a law. And for all of our chemical reactions that we know of to date, this is a thing that is upheld, this law of conservation of mass, provided we can account for everything if it doesn't escape. Okay? So the thing that I'm going to do, I'm going to go over to another scratch pad, that note that we were working on before. And so the way I'm going to take care of this is I'm going to make a little chart. So I'm going to have a reactant side. I'll just call it R. And I'm going to have a product side of this equation, this table. And on the reactant side, I'm going to make a list of all the reactant atoms. So in that first equation, what did I have? I had aluminum, hydrogen, and I'm going to cheat a little bit. Notice that if see how I've got SO4, this sulfate ion, and I've got the sulfur doesn't split apart from the oxygen at all. It remains SO4. So I'm going to treat this as one sort of thing. So on here I've got one sulfate ion. On here I've got three in the products I've got three sulfate ions. So I've got aluminum, hydrogen, and sulfate. And then we're going to account for those things. It's a bit of a cheat, but it helps us keep life a little bit simpler. Sometimes we've got to do that. So I'm going to have aluminum, I have hydrogen, and I have these sulfate ions. Again, let's take a look at, and I should have that on the, I have it on the product side, aluminum, hydrogen, and sulfate ions. Let's go back to this one. I've got one aluminum, I've got two hydrogen, and one sulfate. So 1, 2, and 1. And aluminum, I've got 2, 2, 2, and 3. So I've got 1, 2, and 1, 2, 2, and 3. So let's go back and write that. So 1, 2, and 1, 2, 2, and 3. And then, but the thing, now I look at this and I say, whoa, wait a second, I got way more stuff on the product side than I have on the reactant side. So I'm going to have to start balancing. So let's take a look at this and see if we can find a number, and we'll go through the process of putting these numbers. Now, I can only add molecules, or add the whole particles. So if I have aluminum, if I start off with plain aluminum, I can add more atoms of aluminum. But if I have this hydrogen sulfate, it's like an acid actually. This hydrogen sulfate I can only add more hydrogen sulfate, so I have to add H2SO4. when I get to the product side, this reaction is going to produce aluminum sulfate, but I can only produce more aluminum sulfate. I can't produce sulfate. I can't produce aluminum on its own. It's going to be aluminum sulfate, or and I get hydrogen. So I've got to balance. I can only multiply. I can only add more of the aluminum, or more of the hydrogen. I can't change. I can't change the numbers here. These numbers have to stay the same, because these are the ones that determine the chemical formulas. I'm not changing the chemicals. What I can do is add more of the chemicals to make this reaction balance. So I look at this, and I've got so what if I take the SO4, since I've got 3 on the product side and I've only got 1, what if I multiply this, and I'll do this stuff in red so it stands out. What if I have 3 here, right? So that means I've got 3 sulfate ions, but I've got in the hydrogen sulfate, I've got 2 hydrogen ions for each molecule of hydrogen sulfate. So what I end up with here, I've got 6 hydrogen atoms with my 3 sulfate ions. So let's go back over here. So I'm going to multiply that by 3. So, oh, sorry, let me go do this properly. So I'm going to have, I'm going to change this to, this becomes 6. This becomes 3. So this is balanced. That was good. I've got 6 hydrogens, but I've only got 2 on the other side. But I can fix that. Let's go back to this here. So I've got 6 over here. I've got 2 over here. What if I multiply this by 3? Then I've got 6 hydrogens over here. I go back to here. I say, okay, cool. I've multiplied that by 3, so now I got 6. So that's balanced. The sulfates are balanced. The only thing that's not balanced now is the aluminums. Sorry, let me. The aluminum. Well, the cool thing is aluminum is all on its own. I have 2 over here. I only have 1 here. So if I put a 2 here, now I've got 2 aluminums. I've got 6 hydrogens. So I got, sorry, 2 aluminums, 2 aluminums. I've got 6 hydrogens, 6 hydrogens, 3 sulfates, and 3 sulfates. And so now this thing is balanced, and we can look at our chart over here. Sorry, this became 2 now. So I've got 2 and 2, 6 and 6, 3 and 3. When all these numbers are balanced, we say that our equation is balanced. And now this equation, now with these we call these coefficients in front of it, just like in math. When we put these coefficients in, now the law of conservation of mass is obeyed. Okay, so let's try this with this second reaction. By the way, this type of reaction, the next question, I'm going to answer it now. If I've got aluminum and hydrogen sulfate, and the aluminum now becomes aluminum sulfate, so this aluminum sort of kicks out the hydrogen to stay with the sulfate. So this is called a single displacement. Sorry, I'm going to run. I hope I don't run out of room. Right? Oh, what's happening there? This is a single displacement. Oh, goodness. I'm running out of room here to write. Oops. My apologies. But that's single displacement. I just run out of room in the page there to write. So that's called a single displacement. This one here is called a combustion reaction. This one here is it's kind of neither. And barium hydroxide. No, that's a bit weird. Ammonia with oxygen becomes nitrogen oxide. This is sort of a double displacement, I guess. This one here is a double displacement, and I'm going to run out of time again. Son of a. My apologies. This is crazy. I guess we're going to part 5. We'll see you in a minute.